Hello, good morning, and welcome to everyone joining us for today's webinar, which is entitled Working Platform Analysis Using LimitState GEO. I'm Tom Pritchard, and I'll be introducing you to our speaker shortly and also wrapping up at the end of the session. Today's webinar will provide you with an overview of how you can apply LimitState GEO, which is our geotechnical stability analysis software, to the analysis of a range of problems involving working platforms. Amongst the topics that we'll go through today are an overview of working platform analysis, some principles of computational ULS analysis, and also working platform analysis, including sort of layered soils, stability near slopes, things like that, using LimitState GEO. The webinar is scheduled to last around an hour and will include some time at the end for questions. These can be posted via the question functionality that you should have in the webinar interface in front of you. We do try to answer as many of your questions as we can in the time available, but if we don't get around to yours, or if you happen to think of something after the event, you're more than welcome to contact us outside of the webinar via info@limitstate.com, and we'll be happy to answer these in detail for you. Before we start today's proceedings, I'd just like to ask you a quick question, which is how did you first find out about LimitState GEO? You should be able to see a poll in front of you on your screens, and all you need to do is click the option that you feel is most appropriate. If the answer is none of the above, then obviously please leave it blank. I'll just leave it up there for a few more seconds before we get on with things. So thank you. Without further delay, I'd like to welcome you to our speaker for today, who is Dr. Colin Smith. He's the LimitState GEO Product Manager, and I'll now pass you over to him.
Okay, thank you, Tom. Good morning to those of you in the European time zone, and good afternoon or evening for those of you joining us from elsewhere in the world. As Tom has mentioned, my aim today is to show you how LimitState GEO can be used to analyze working platform stability problems, and as with previous webinars, I'll be using a mix of slides and the software to illustrate the key points, and we'll look at a mix of basic principles and some example problems. Following a brief recap on the principles of working platform analysis, we'll look at a mix of ultimate limit state analysis principles and how to use the software to solve a range of problems. Layered soils, looking at the influence of water table, stability of platforms near slopes, and the use of geosynthetic reinforcement in working platforms. As this is a problem-specific webinar, I will focus on how the software can be used to solve the working platform problems, so I may skip over some of the details about how to use the software, but hopefully the process should be clear. For those of you who are new to this webinar series, I think it's useful first to give you a brief context of the software and to the company LimitState. The University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And the company was spun out of the University of Sheffield in 2006 with the aims of making this research available to industry. Now, of course, industry users not only want powerful tools, but also ease of use and support, which is what LimitState provides. And LimitState also has sophisticated testing systems in place that mean every time we modify the software, over 800 tests automatically run to make sure that the software does what it's supposed to do. The company currently has 2 products at present, LimitState Ring, which is for masonry arch bridge analysis, and LimitState GEO, which is the subject of today's webinar, and there's several more products in the pipeline. So just to set LimitState GEO in the context of currently available software, on the one hand, we have software based on conventional approaches such as method of slices for slope stability, which do a pretty good job for that particular problem. And for more complex analyses, you might be using finite element methods, which could deal with any problem geometry and complex soil behavior, but typically requires a lot more expertise to use. Filling the gap in the middle is computational limits analysis, which provides an ultimate limit state analysis capability with the geometry flexibility of finite elements, but the ease of use of the traditional approaches. Typically, the only parameters you need are the cohesion, angle of friction, and unit weight of the soil. And this is essentially what LimitState GEO provides. And these mechanisms just illustrate the range of the capability of the software. You could determine the collapse state for any problem geometry, and you can model slopes, retaining walls, structural elements, and soil reinforcement, as shown in some of these examples. But today we're going to focus on working platform design. So before we start using the software, I'll just recap on some of the relevant key principles relevant to today's webinar, and then we'll look at the actual analysis approach. So clearly working platform design requires consideration of a range of issues such as safety, practicalities, but also analysis of the actual platform. And documents are available which cover the whole set of issues. So for example, in the UK we have a guidance document BRE470. What I'm going to focus on in this presentation is only the design or analysis calculations. We'll assume that we're using design values of parameters so that any factors of safety have already been incorporated into the design. So we're going to focus purely on the analytical side in this webinar. Now typically, obviously a working platform comprises a layer of granular fill, relatively strong granular fill, overlying a weak subgrade to give us a platform that is stable. And in simple terms, the aim is to try and spread the load from a vehicle, for example, laterally through the platform to reduce the pressure on the subgrade and prevent local collapse or bearing capacity failure. Now, there are various methods of analysis proposed in the literature. One of the simplest is a punching failure analysis, where it's considered that a block of soil underneath the load is pushed down through the platform and then acts on the weaker subgrade. You get a standard bearing capacity failure in the weaker subgrade due to that force. But on the sides of this block, we will have shear forces acting upwards, so they provide additional resistance, and that then reduces the loading on the underlying subgrade, and we get an enhanced bearing capacity. This is one of the methods illustrated in the UK document BRE470, and you get a formula that looks like this. I'm not going to go through it in detail, but it basically incorporates subgrade bearing capacity with a term which deals with the transmission of the load through the platform and the reduction of that load as it goes through the platform due to those shear resistance. Other analyses look at the problem in a slightly different way, so you could consider that as the load comes down, the load is spread out laterally, but that it also applies a shear stress to the surface of the subgrade. That shear stress combined with the vertical load will actually lead to a lower capacity in the subgrade, and the soil is not only pushed downwards but sideways, and so you get a reduction in bearing capacity due to that, but you have got the load spreading as well. Those are all sort of semi-analytical approaches. If we actually look at a computational limit analysis solution, which is what LimitState GEO software produces, basically gives you a collapse mechanism. And in this case, you can see that this is a mechanism for a granular platform overlying a clay soil in this case. And we have a clear punching mechanism in the center, a rigid block of soil pushing down, the soil in the clay moving sideways, but pushing that granular soil upwards to the sides. So we're getting the central punching failure. We're also getting some load spreading. This is showing the kinematics, but the load is still being spread sideways. And then we're getting resistance from the overlying fill as the clay tries to push upwards into it. So those are all dealt with inherently in the analysis, and the analysis is actually seeking the optimal collapse mechanism for that particular problem. So that's a brief overview of the basic sort of issues in the mechanics of the working platform. We'll now have a look at the software and how we can set up some problems. So This is the typical, if you haven't used the software before, the interface. We have a number of windows, the main viewing screen, a materials explorer where we can create and use different soil materials, and a property editor on the right where anything you click on in the software, the properties appear there. But we'll go through that as we go through the software. To start with, we'll create a new project. Now you can create an empty project and draw your own geometry, or there are some built-in wizards to produce some standard problem geometries. For a working platform, we'll kick off with just a simple footing. So I'll click OK to that. You get an opportunity to put some general information about the project, which we'll skip over. We'll look at the geometry here. So we're just going to model a footing of width. Now we'll imagine this is a tracked vehicle, so maybe we'll take a 0.7 meter width footing. The soil layer thickness I'm going to make fairly thick to accommodate later adjustments, and the width of the soil also fairly large to make later adjustments. The underlying soil, well, we'll just model a footing on the subgrade to begin with, so we'll work with a fairly weak clay, undrained strength of 24 kPa, unit weight of 20. The footing we're just going to model, or the track, we're going to model as a rigid block. We don't want to be applying a flexible load because they will always collapse. The theoretical collapse on a granular soil is always zero load. And then we'll just finish there. And that produces the geometry. It's fairly simple geometry here. So this is where our load is coming through. This is our underlying soil. And as I said, anything we click on, we can see the properties. So if I click on the load here, I can see the properties of the load at the top here, and this has been set to a permanent load. The loads can be specified according to the Eurocode distinctions. And what I'm going to do is set a pressure of 150 kPa as the load on that track or footing. And we have this setting called adequacy, true. The way ultimate limit state software works, it always seeks out the collapse mechanism. So anything that you model may or may not be at the collapse state, so the software has to increase or decrease some parameter to get us to that collapse state. In this case, by setting this value to true, what we're asking the software is what do we have to multiply that load of 150 by to get collapse in this problem. So that's pretty much it set up. The only other thing I need to look at is what's going on between the block and the soil. We have a little interface here. So you can model the interface between different bodies. And so here we're modeling the interface between the track and the soil. And we could choose to have a different friction angle or cohesion there. So here we've actually, the wizard has set it up that we have half the cohesion or half adhesion strength on that interface compared to the parent material, which has been set to be the footing soil. So that's basically the underlying soil. So we're assuming roughly half, but that can be changed to any value you like. Once the geometry is set up, we just click this button here up at the top left, solve, and the software will quickly determine the critical collapse mechanism. Now and animate it. So what you can see is it's generated something pretty close to a Prandtl failure mechanism. It's slightly a coarse mechanism. This is to do with the resolution of the solution that we're working with. We're actually working with what we call a medium nodal density. If I just preview the nodes, we'll look at this later, but basically we put a set of nodes in the problem, and the slip lines that the software will consider are those that connect these nodes to any other node. So what we do normally is to use the software in a very interactive way to get quick solutions. We'll work on a fairly coarse or medium nodal resolution, and then when we come to want to pin down the collapse loads, specifically we'll then move on to a higher nodal resolution, but that obviously takes a little bit longer to solve. So here, what the software is telling us is that this track will sink into the soil, and actually, in order to stop it sinking into the soil and to be just on the point of collapse, we have to multiply the load by 0.85, so that's this number down here. So that means the load is too big. It needs to be reduced to get us to the point of collapse. At the moment, it would be beyond the collapse state, so it's overloaded. So you can think of that number in this context as a factor of safety on the load. And this number that we'd get is very close to what we get if we used the classic bearing capacity theory of 5.14 multiplied by the undrained shear strength would give us very close to this number. So we assume we've now decided that this track vehicle cannot sit on this subgrade, so we want to be putting a platform material on. So maybe we'll think we've got some platform material with it's a granular material with a strength of 40. So we could create a new material. So we go Tools, Create New Material. A more cooler material. I'll call this platform. Give it a slightly different color. And it's going to be a drained soil. We'll give it an angle of friction of 40, and we'll give it a dry and saturated unit weight of 20. So that's been created. That now appears here in the Materials Explorer. We can just drag and drop that onto the body that we're interested in, replace it. So now we've got the foundation sitting on the platform material, and we just check that that platform material can actually support the load that we need it to, because there's no point using it as a platform material if it can't work on its own. We also need to check the interface material. This interface material is still set for the clay, so we need to create a new interface material. I can take this platform material and duplicate it. It gives me a copy of platform. I click on that. Its properties appear over here in the window on the right. I'll call this platform interface. And let us say we have half the angle of friction of the interface. It may be larger than that. And I forgot to just change the color slightly so we can distinguish it. So I can drag that and drop that on the interface here. And so now we've got the new problem. If I then solve that problem, I get a collapse, an adequacy factor of 5.642. So that means that I could multiply that predefined load of 150 by 5.6, and that would bring the system to the point of collapse. So effectively, I've got a factor of safety of 5.6 on the load. So that's perfectly okay. So the platform on its own is fine. What we're interested in, of course, is whether that would work as a platform. So let's assume that we maybe try a 0.4 meter thick platform. We could just split this layer of soil up across and set this thickness of this body to 0.4. The top of the body is actually at 1.5, so I need to set the bottom at 1.1. So I've clicked on the actual layer, and its properties appear in the property editor up here. There's a geometry editor down here, which gives its geometry, so I'll set the y-coordinates to 1.1, and so now we've got a separate 0.4 meter length there. I then can drag and drop the original soil, which was that clay soil, and put it below, and solve that. So that's now effectively the platform design. We get a different mechanism with that punching failure into the clay and then deformation around that. And in this case, we get an adequacy on the load of 1.08. So we would say that that design is now adequate. We assume we've already got safety factors applied to the parameters we've entered, so that is just slightly over-designed. As I said, we normally, if you're working interactively, just trying to get a feel for the problem, you work fairly coarse nodal density. We can change the nodal density here, say to fine. That will increase the number of nodes used. I'll just solve it there. It'll take a little bit longer, and we'll just see what effect that has. But normally you would just increase the nodal density and see that you're getting very minor change in the capacity, and then you've basically got the critical answer. So here it's gone down slightly to 1.05. You get a slightly more refined mechanism in that particular case. So I'll just revert back to medium just to make sure that the process is fairly quick for the purposes of this webinar. So 0.4 meters turns out to be thick enough. We could say, well, can we get away with 0.3 meters perhaps? So I can increase the thickness of the layer to that point and rerun. And in this case, our adequacy factor is actually coming out slightly below 1. 0.98 it's saying, so that isn't adequate, and we would have to use a thicker layer or a stronger platform. Okay, so we'll revert back to the 0.4 meter depth. This has clearly been analysing a granular platform over clay material. We maybe have situations where we have a granular platform over another granular material which is weaker, so we can look at that. We'll just take one of the built-in materials. There's a built-in material called loose sand. If I click on that, its properties appear on the right, and it has an angle of friction of 30 degrees, dry unit weight of 14, saturated unit weight of 19. So I can just drag and drop that onto the lower area, and now I've got a stronger granular layer over a weaker layer. If I solve that, see what happens. And in this case, I've got an adequacy of around about 1.7, so that particular combination would actually work. We'll just look at a pre-set up problem, which is very similar to that one. So it looks almost the same. All I've done is I've made that material, it's called subgrade, and essentially it has a slightly lower angle of friction of 25 degrees in it. Everything else is the same, so I'll solve that. We see what we get. So here we've got a reduced adequacy factor, but of around about 1.1, but that is still above 1, so it's still acceptable. We can still increase that load a little bit before we get collapse. Now, with granular soils or drained analysis, we may be concerned about the water table. So if we have a water table in this problem, at the moment we're assuming the water is well below the subgrade, but that may rise up, or we may have a situation where the water table is close to the original soil surface. So we can put water table in quite easily. There's a range of options for putting in water, but we just assume we've got a simple horizontal water table. So I can click this button on the bottom left, which is draw the water table, and just draw a water table across. So I'll put it fairly close to the surface of the original subgrade level. And if I click on that, I can see its geometry here. I'm going to just make sure that we put it up to about 0.5. Okay, so that's now working. So everything below that will be using its buoyant unit weight. And again, we can solve the problem. In this case, it doesn't make a huge difference to the load capacity. Most of the capacity is coming from the upper layer, and the part that's coming from the lower layer, we've gone from a dry unit weight of 14 to essentially a buoyant unit weight of 9. So that's had a small effect, but not a huge effect on the capacity. But we can vary that water level as we wish, and or have it inclined if we wish, and resolve to see what those effects would be. So I'll just clear that water table, remove that. The other thing, of course, that is of interest on this sort of problem is perhaps how close can we get that load to the platform edge. So I'll just draw in by hand roughly a platform edge. So I'm just drawing a line across that boundary. Then the bit I don't want, I just select it and press the delete key, and that vanishes. So now I've got a foundation at the edge. If I click solve on that, we see the software now gives us a very different mechanism to what we had before, and a much lower adequacy factor of 0.54. So that has significantly dropped and is telling us we can't put that load that close to the edge. Now we may want to see, well, how close can we put it? So we can move the load around. Easiest way to do that is to actually just drag it by hand. If we click this bottom at the base called ortho, that forces any movements we drag with the mouse to be vertical or horizontal. So if I select that and just drag it sideways, it will just move horizontally, and then I can solve again and see if that's moved far enough away to give me an adequate load. Again, it hasn't. I'm only gone up to 0.65, and so it's not going to work. So I'll try and drag it a little bit further over and see what we get in this particular case. So that's brought it up to 0.85, which we're getting closer there. So we could carry on with that sort of process, move it around, and explore where we could put that load, or we may decide we want to put in a thicker platform area. So hopefully you can see the flexibility of the software and the interactivity. You can move the parameters around, change the geometry, do what-if calculations, just get a feel for what's going on. It's also very easy to add in other layers of soil. We can just draw in other lines, for example, and put in different soil types in those particular cases. What I'll do, rather than do that, I'm going to revert back to our original geometry. So we have redo and undo buttons up here. So I'm going to undo and get us back to that original state. And one of the other things, of course, is your working platform may not be fully horizontal. You may have ramps or a sloped area, so you can look at the effect of that. So I'm just going to do this crudely by hand. Just drag that boundary down a little bit, drag that one up a bit. So we're now sitting on a slope. Analyze that particular problem, and clearly the mechanism is going to be skewed to the right, in this case downslope, and we've got a little bit of loss on the adequacy factor. It's coming out at around about 0.98 in this case, so it's come down from about 1.08. So in this particular case it's below 1 and it's not satisfactory. So again, we'd have to increase the platform thickness if this sort of slope was to be encountered. Okay, so that's kind of fairly quickly gone through range of options in terms of using the software to explore working platforms over clay, over granular material, with slopes, looking at the edges with a water table. What I'll do now is we'll just revert back to the slides briefly and just recap on what the software is actually doing, how it works, so that it's important to know how that is operated to get the most out of the software. So back to here. So we'll look at how the software works. It uses a method called discontinuity layout optimization, which provides rigorous upper bound plasticity solutions. And it's a rapid and direct means of analyzing the collapse state, unlike finite element incremental methods where you increment to a collapse state. This is a direct method which uses optimization to go direct to the collapse state. Came out of a 5-year EPSRC-funded research project carried out at the University of Sheffield, and the core publication was published in the Proceedings of the Royal Society in 2007. There have been a range of publications thereafter. How it works is very simple in essence. Here's a very simple problem. We've got a load sat on a block of soil with rigid boundaries to the base and to the left. unlike finite elements, what we do is we populate that domain with nodes. So here I've got 12 nodes in the domain. We then connect every node to every other node with potential slip lines. So I will have, in this case, 12 times 11 over 2 is 66 possible slip lines. And we feed those into an optimizer, and the optimizer selects from that set of slip lines the most critical mechanism that it can build out of that set. So in this particular simple case, if we feed that to an optimizer, we get this simple mechanism with 6 slip lines forming 2 sliding blocks. And that then is displayed by the software, and that's a collapse mechanism that is given. Now, with only 12 nodes, you get a fairly crude mechanism. The more nodes you put in, the better it is. So we've been working with most of the examples I've shown 500 nodes, but you could go up to 1,000, 2,000, 4,000, 5,000 nodes. So if we're using, say, 4,000 nodes, you are looking at roughly, let's say 1,000 nodes, you're looking at 500,000 potential slip lines. If you look at 10,000 nodes, you're looking at 50 million, I think, potential slip lines. So you get a lot of slip lines, and the software is going to build the failure mechanism out of that. It turns out that the way that's formulated is a simple linear optimization problem, and there's some very powerful linear programming solvers available which are built into this software. That gives us our solution in terms of slip lines. The software then takes all the slip lines that are identified and finds the solid blocks between them and animates that to help interpretation. The animation is strictly only valid at the instant or the point of collapse, but of course to make it visually clear, the animation will take that beyond that point so you can actually see what's going on, but strictly it's only valid at the point of collapse. So if odd things appear in the animation, such as down here with this block sliding upwards, the little corner appearing, that's just because the animation's been taken beyond its immediate state. So the key point really is that, as I mentioned earlier, increasing the number of nodes allows more potential slip lines and then more precise mechanism. But working on the sort of medium nodal resolution, medium to fine, you can work pretty quick and interactively with the software. But when you come to the final analysis, we recommend you move to a higher number of nodes. So we've clearly seen this simple type of analysis. This is a foundation on clay, which is a problem we started with. We get to within 1% of the exact solution in about 1 second with this. And one of the nice things about this numerical method, discontinuity layer optimization, is that it can identify mathematical singularities in the solution without difficulty. That it's just an inherent part of the method. There's no special cases, and finite elements can find this more difficult to deal with. So these are cases where all the slip lines meet at a point, and in theory you have a lot of different stress states at one single point. But as I said, this method deals with that inherently, and there's no extra programming or anything like that required for that. And these do come up quite often in limit analysis problems, particularly at the corners of, say, foundations or retaining walls. Obviously, you want to be sure the software you're using is verified. So we, as I mentioned before, we run many tests on the software, and a lot of those are actually compared back to solutions in the literature, and we compare what the software produces with what the literature solution is, and we've got over 100 of those available on the website. So, for example, this one's actually for a trapdoor and anchor problem in clay, and the benchmark in the literature was 17.07. With a fairly coarse set of nodes, the software gave 18.1, so it was out by 0.7%. But there are a whole range of other ones that can be viewed on the website. Okay, now clearly the software is a plain strain software, and in many cases in your working platform design, of course, your tracked if you've got a tracked vehicle, for example, that's going to be a rectangular load rather than an infinitely long distributed load. So in working platform analysis, many of these sort of conventional formulas will include shape factors, and that shape factor changes according to the aspect ratio of the load. There doesn't seem to be a lot of literature on variation of shape factors on layered soils, and in fact there's not always that amount of agreement on shape factors for just single layers of soil in the literature. So it's hard to give any specific advice in this case. I think in the absence of other data, I would say it would seem reasonable to use the lowest of the shape factors calculated for each layer. That would be certainly a conservative approach, but obviously you'd have to take judgment, for example, where you've got asymmetrical failures or near platform edges. Those sort of standard shape factors are not going to work. So it's hard to give any more specific guidance there in this particular case, but I do appreciate, of course, the software is a plane strain analysis. Clearly 3D analysis would be a lot more complicated to set up. Okay, we now just move on to use of geosynthetics in working platforms. So we'll just have a quick look at the sort of theory. So this is the same diagram I showed before, but I've put there's a big red line between the platform and the underlying soil, which is indicating a geotextile or geogrid. The key thing about this is that it's a way of transmitting shear stresses from the soil to other parts of the soil body through the geotextile. And in this particular case, it's beneficial. We have our load coming down. There is some shear stresses applied sideways through the platform. Now, rather than transmitting those to the underlying subgrade, if they're transmitted into the geotextile or geosynthetic, and that carries that shear stress, then the underlying soil is not loaded in that way and therefore can actually produce a larger bearing capacity. So that's one benefit. And as the mechanism of failure in the subgrade comes around, as it wants to push up through the geotextile, there's going to be a resisting shear stress there as well, also carried within the geotextile and able to be transmitted further out, and so that gives us an extra capacity. So those kind of mechanisms are present and don't rely on membrane action. So membrane action is where that geotextile would actually be a curved shape and then able to take some load in tension that is a vertical component. We're just going to look at the action of the geotextile in this particular case, where it's just taking those shear stresses and transmitting them elsewhere and preventing them being applied through onto the subgrade. So we'll just revert back to the software and I'll just grab a pre-prepared model. So here we've got a very similar model to the one before. We have a load of, this time we've got a load of 1 on the track or the foundation. In this case, it works exactly the same. The software will give us an adequacy factor. Basically, it says what do we have to multiply that unit load by to get collapse. So the number we'll actually get will be the collapse pressure on that foundation or track that is required. So rather than treating it as a factor of safety, we just treat it as the actual collapse load. It's sitting on a soil here. The platform soil here is 40-degree soil, and the underlying soil here, the subgrade, is a clay undrained strength of 24 kPa, unit weight of 20. So we'll just solve that first to see what answer we get. And in this case, it's coming up with a bearing capacity of around about 182 kPa for that particular sensor system. Now let's assume that that's too low, that we've got a vehicle which has got a higher load than that to be applied through the tracks. So we say, well, let's, rather than adding more material to the platform, let's investigate a geosynthetic. So we can create that using what's called an engineered element in the software. So if I go Tools, Create New Material, rather than creating a more Coulomb material, which is for soils, I'm going to create an engineered element. I'll call that Geosynthetic. Give it a distinctive color. Let's make it red. And there's some pre-built-in sort of guidance for typical uses of engineered elements, which were originally set up to model soil nails and sheet pile walls. In this particular instance, paradoxically, I think the sheet pile wall can yield is the closest thing that will get us to what we want, and we'll modify the properties accordingly. There are properties called interaction and structural. The interaction here, pull-out factors and lateral factors are really only relevant to soil nails. If we set these to a very large number, effectively infinity, then they allow us to model a sheet of material which soil cannot pass through. So we don't need to worry about those numbers as long as these two numbers are very large. That's fine. Plastic moment is for, say, a steel sheet pile to allow it to model bending. For a flexible geotextile, we're going to just have a plastic moment of 0. And we'll just click OK on that. So that's created our geosynthetic. We can see the properties here. These interaction parameters very high. Moment of resistance 0. We also have to change things here. So the rupture strength tells us what tensile stress or tensile force the geotextile can take. I'm going to set that to 15. And the compressive strength is what it can take. Of course, a geotextile cannot take any compressive strength, so we set that to 0. And we have a thing here called post-solve display. It's set to moments at the moment, which is useful for sheet pile walls, but I'm more interested to see the tensile force in the geotextile. So I'm going to just set that to view the tensile forces. I can then add that geosynthetic. Because it's a one-dimensional object, I can add it not to solids but to boundaries, so I can drop it on this boundary, and now this boundary contains that geotextile or geosynthetic. At the moment, if I click on that, we can see the materials here. We've got top, engineered element, and bottom, so we have the engineered element in the middle. The top and bottom can be set to interface materials if we wish. So typically for a geotextile in a soil, we might have a coefficient, friction coefficient of, say, 0.6 to 0.9, something of that order, allowing for the fact that we're not going to get the full strength of soil when interacting with the geotextile. I won't actually set those at the moment. We'll just assume there isn't any, so it's going to model the full friction on the top and the full cohesion on the base. So if I solve that, see what result we get. Actually solving this on fine just to give us a slightly more refined mechanism. And we see that the load has increased. At the bottom here we can see that it's homing in on 231. Before we had 180, so we have in fact increased our capacity by about 50 by adding in that geotextile. And that, as I said before, is purely because it can take those shear stresses and prevent them being transmitted through from the upper material into the lower material, and therefore we get more capacity out of the lower material. So we've animated it. You can see the distortion. And what we've got plotted here is the actual force in the geotextile. So actually, as we hover over each block, we can see what the force is, and at the edges here, that geotextile is actually being pulled and ruptured. So it's been taken to failure in this particular case. If we wanted to investigate what would happen if we increase the strength, so maybe I'll increase that to 50. So that's the rupture strength of the geotextile I've increased to 50, and solve again. Then we would expect to get a larger load capacity because we're not going to be failing that geotextile and so on. So of course that we're at the point of failure. The system is failing the geotextile at that particular load. At lower loads we wouldn't be failing the geotextile. So in this case, the mechanism actually gets even bigger here. In fact, the mechanism has expanded to fill the boundaries of my model. If the mechanism does touch the boundaries, and these are artificial boundaries rather than being solid rock at the sides, then the solution is not going to be correct. It's going to be overestimated, and one would need to extend the boundaries, move those sideways and downwards in order to get a correct solution. So here we get 267, which will be a bit of an overestimate. We can see that the tensile forces in the membrane have been spread out more, but have actually in the middle reached pretty much that 50 as well at the edges. So as I said, this is not a valid solution. We wouldn't accept that, and we would want to kind of pull these boundaries out. We can drag them out by hand or redraw them and resolve. I won't do that now, but that would be necessary. And I just recap that this enhancement due to the geotextile is due to that shear transmission. It's not membrane action. We'd have to model a geotextile that curved down. I won't do it properly here, but we can add nodes to here and kind of get a curved shape, draw in a curved shape, or we can import geometries as well into the software from DXF and so on. I'm still on the ortho setting here. But once the geotextile has an inclination on it, then of course the tensile forces transmitted to that have a vertical component which could react against that. But normally we're not going to model that in this software. Okay, so that hopefully shows you how we can model the influence of a geotextile in the problem. So we'll flip back to the slides and just wrap up with a recap on what we've looked at. So key concept with the software in terms of the ultimate limit state is that clearly anything you design is inherently stable and is nowhere near its ultimate limit state. If you want to undertake an ultimate limit state analysis or a limit analysis, you have to drive the system to collapse by some means. And you can do this implicitly or explicitly. In many conventional calculations, it's often implicit and you don't realize that's what you're doing. In a numerical analysis, you have to do it explicitly. So in this software, the way we've been working it is basically to ask the question of the software, how much bigger does a load have to be to cause collapse? Or by what factor A do we need to increase that load to cause collapse? And that we call the adequacy factor on load. And loads can be applied surface loads, or they can be self-weights as well. The other way we could look at the problem, which is perhaps less relevant for working platforms, we're probably more interested in the actual load applied by our vehicles, is we can say how much do we have to reduce the strength of the soil by to get collapse, and we can do that, and then the adequacy factor that the software would give us, we haven't actually demonstrated, is a factor on strength essentially. But essentially, if the adequacy factor is bigger than 1 and you've put in all the sort of design loads and design strength, then the system is stable. If it's less than 1, the system is unstable. And it can be interpreted as some kind of factor of safety, factor on load, or factor of strength, or an over-design factor if you're using partial factors. In terms of working platforms, we've seen that we can model layered soils. So this is just the mechanism for the clay subgrade. This is actually one of the examples from the UK document BRE470. We actually did a comparison of the two methods of calculation for the clay subgrade problem, and get a pretty good agreement between that and the semi-empirical formula given in BRE470. So this just shows the variation of predicted bearing capacity against undrained shear strength for that example problem that's given in the document for a specified geometry. I've mentioned we can model 2 layers. We can easily model 3 or 4 layers if they happen to come up. It's a very straightforward extension of what we've done already. And hopefully you've seen that we can model the edges of platforms or slopes and get an appreciation of the reduction in capacity that those will bring. You can, of course, model more complex loading scenarios. I didn't look at this one because it's rather complicated, but here we've got a vertical load and a horizontal load, and we've got 4 loading positions, and the whole vehicle is therefore causing a combined failure mechanism. So that can be done quite straightforwardly. This could be a very simple set of rigid bodies up here just linked. This is just more for aesthetic reasons that we've drawn it like a vehicle, but you don't need to go to those lengths in this particular case. So to summarize, hopefully you've seen that working platform analysis is straightforward to undertake in LimitState GEO. We can model multi-layered soils, slopes, platform edges, and water table variations. The analysis is plane strain, so you have to use judgment and using appropriate shape factors for the particular scenario that you're modeling. And that geosynthetic reinforcement is straightforward to include, and its ability to redistribute those shear stresses leads to an enhanced load capacity. Finally, I'd just like to wrap up. Hopefully you've seen as we've used the software that the software is interactive and solved quickly, so you can use it very much to answer what-if type questions, explore the parameter space, and just get a better feel for the problem. And this one piece of software can solve any ultimate limit state problem type, so you don't need to put in idealizations or correction factors for non-standard geometries or try and learn many different pieces of software. This model working platforms, slope stability problems, retaining wall problems, etc., which clearly we haven't had time to look at in this particular webinar. So that completes today's webinar. I hope that's been informative, and we've got a few minutes. I can take some questions if there are any questions. Okay, so running through the questions. Question saying the analysis does not include any partial factors and they need to be calculated before the values are input into the program. In the examples I've been looking at, this is the case. I've not been including any factors. The software is set up to allow you to put partial factors onto parameters. So we have what's called a scenario manager, which I'll bring up on the screen here. And it allows us to put factors on permanent loads, variable loads, accidental loads, and on material properties. So if the kind of approach you're using, such as Eurocode, fits in with that, then you can choose. So for example, here I'll bring up design approach 1 combination 2 in Eurocode. You can set that, and then what the software will do is before it solves a problem, it will pre-multiply all the loads by these factors and pre-multiply all the strengths by these factors. So you can set it up using this facility to pretty well do all the partial factoring for you, in which case you can enter characteristic values into the software and get them factored. Alternatively, you could just put design values directly in and work with those directly and just revert back to a use of Unity partial factors. Okay, I got a question on how far does the lower boundary need to be from the applied load. Essentially, in the upper bound analysis, if the mechanism does not meet or touch your boundary, then it's far enough away. So as soon as that the mechanism hits a boundary, if it does, you need to move the boundary downwards so that you're clear that the mechanism is fully within the soil body, unless, of course, your lower boundary is sat on rock, in which case you may be happy with a rigid boundary. Okay, got a question on track loads are often non-uniform. Can non-uniform loads be input into the software? So you can, for example, take, let me just delete that load. Well, I can either set part of that load surface to say a half, part of it to 1, or I can just eliminate that load. So you can split the loading surface anywhere you like and apply different loads like that. and of course you can apply as well if there are horizontal loads such as wind loads coming down to your foundation. You can put in shear as well and have inclined loads. So there is a facility to incline the load or offset it, and clearly, depending on the way you've set it up, that will model a particular moment combined vertical moment loading. Square pad loads, can they be analysed rather than strip loads? Unfortunately not. This is a plane strain software. To do square pad loads is a fairly complicated 3D analysis, so you'd have to adopt a shape factor and apply that to the loading that we've got there. Are there any future proposals to update the software to include shape factors? It's hard to include shape factors for every scenario. Unfortunately, every scenario will have a different shape factor, and if you've got a layered scenario, then they will have a different shape factor to a different layered scenario. It will depend on the combination of the soil types that you have, and as I said earlier, there isn't even agreement on the shape factors that you should adopt for uniform bodies of soil. So the best that one could do is provide draw from the literature what sort of shape factors are available for layered soils, but as far as I'm aware there is not that many, and unfortunately you can't use one shape factor to cover all aspects. So as I said earlier, it would seem reasonable in most cases to adopt the lowest value of the shape factor for your particular layer, for the layers, each individual layer of soil, but unfortunately it is a complicated issue, and with a plane strain analysis it's not easy to provide a one case fits all for all different possible combinations of layers. So it's very unlikely to appear in the software, I'm afraid, but we may provide sort of additional guidance on the sort of factors that are available for particular scenarios. Can surcharges be modelled as well as load cases? So if you've got a surcharge on the soil here, we can model, for example, a constant load. So if you've got, say, a 10 kPa surcharge, and you could do that for adequacy equals false, and that just means that the load is just a constant fixed value. And what the software is doing is it's trying to find when it has to multiply the load that's represented by these red arrows by to cause collapse, but this surcharge remains fixed at 10 kPa. So surcharge can be straightforwardly modeled. Influence of the interface layer underneath the applied load. So I mentioned there was a layer here. Now when you have a foundation or a track sitting on a soil, it's not necessarily going to be able to mobilize the full friction between itself and the soil. It very much depends on the nature of the material of the foundation or of the track. So there should be guidance. You hopefully can get some guidance on for a particular type of track what that is. What I would say is that certainly for granular soils, it's generally accepted that if the friction here is more than 1/2 of the friction of the soil below, so if the soil below had a 40-degree friction, as long as the friction between the track and the soil is greater than 20 in this case, then there's very little difference between 20 degrees and 40 degrees. You can try that out in the software, but it's generally been found, certainly for uniform granular layers, that between 1/2 and the full value makes very little difference. But it's something that you can look at parametrically to have a look. So typically, I think you'd normally model that. You can model it as 1/2 to be on the safe side, but there's not going to be a lot of difference moving up to the higher frictions. Question about acceptability of rupture strengths in geogrids. Again, it's not really my place to give advice on uses of factors of safety of geogrids. Clearly you need to take account of the strains that are acceptable before you get to yield. and obviously the factor of safety, but that very much comes down to the design code that you're, or design guidance that you're working with. So I think you have to take that from there. Can we incorporate the use of timber mats and beams in platform design? You can incorporate rigid blocks. So if you, this is type of analysis we're doing with is an ultimate limit state analysis. So as long as you're happy to model your timber mats as a rigid inclusion, you can include those in there. You simply would just draw in a, I don't know where you're thinking of having it, but you could draw in a rectangular block and make that a rigid element and see what happens. Or it may be in the other axis. Seismic analysis. It is possible to do seismic analysis of software. We have seismic actions here, so you can actually apply horizontal and vertical accelerations and see what effect that actually has on the load capacity. So you could either set in a fixed value, or you can actually say to the software what size of horizontal acceleration will cause collapse. There isn't really time to go into that feature, but you can certainly apply pseudostatic seismic analysis. Okay, so running short of time, just wrap up on the last few questions. Yeah, the question about modeling interaction between two adjacent track loads. So yes, that will be modeled. You can draw in more than one track load, and the interaction will be modeled correctly in plane strain. I think the other questions I've probably already addressed in terms of the shear resistance between the geotextile and the soil. You can modify those interface frictions if you wish. The example I showed, we assumed full friction, but it's straightforward. In the same way as we've got the interface material below the track or the foundation, we can do the same with the geotextile. And one question about what does a 3D button do? That simply gives you renders a plane strain problem in 3D. It doesn't do a 3D analysis for you, unfortunately, but that hopefully answers that question. Okay, I think we've got to the end of the time. So thank you for those questions, and I hope you found that useful. So I'll pass back now to my colleague Tom to wrap up.
Thank you, Colin, and thanks everybody for attending. We hope you found the webinar informative, and as mentioned at the start, if the presentation sparks any questions that we haven't already answered for you, then please get in touch via info@limitstate.com, and we'll be happy to answer questions for you in that way. For those of you who aren't current users of LimitState Geo, we'll be in touch over the next few days just to get some feedback and find out if you do have any further questions. And for any of you who would like to watch the webinar again, or if you think you might know somebody else who might be interested to see it, there'll be a recording available later today on our YouTube channel, where you'll also be able to find recordings of the past webinars in this series, as well as some other useful movies. We'll email you with the link once this is available. This is the last in our current run of scheduled webinars, but it's very likely that there will be more in the relatively near future, so please do look out for these and other events on our website, which is www.limitstate.com. And finally, I'd like to say thank you to everybody for listening, and hope you can join us again in one of our future sessions. Goodbye.